Welcome back to eCoreAcademy, everyone. My name is Anita, and as you all know, I am a teacher and co-founder here. I hope you're all having a great day, and as you can see, I hope I can make it even better with this new Biology 1 lesson I have for all of you. In this video, we're going to be continuing the atoms, bonding, and molecules, so hopefully you've seen my part 1. If not, it's going to be linked in the description box, so I highly suggest you check that out. This is just going to be a part 2. We're going to add to it by looking at the chemical properties of matter. We're also going to look at some physical properties, but mostly we're going to talk about the chemical composition, chemical formula, balancing chemical formulas, etc. And then we're going to talk about the parts of the atom, including the proton, neutron, and electron. But before I even get into the video, I do want to explain something. You might be wondering, why are we talking about chemistry-related subjects? And that is because this is going to be kind of an introduction to our first unit, which is all about biologically important macromolecules. And in biology, the course is structured in a way that we start from these smallest molecules to large ecosystems. We build and we build and we build. Therefore, to understand how these macromolecules are built, you're going to have to understand chemistry, you're going to have to understand atoms and the way they bond, things like that. So that is why we're talking about biochemistry. I also want to point something out, and I hope you all like my new hoodie. This is eCoreAcademy.org. This is customized merchandise. I really hope you guys enjoy. I hope you guys like this print, and hopefully we can make it available to the public one day. So keep your eyes open for that, and let me know in the comments down below. Do you like this hoodie? And if so, let us know, and then we can arrange for the public to have to be able to buy our merchandise as well. But before I get into the lesson, I'd really appreciate it if you all could hit the like button, the subscribe button, the post notification bell, drop a comment down below, and share using our socials. So let's get right into the video. This first slide is going to be talking about the properties of matter. And like I said before, we're going to be looking at the physical properties of matter, but we're mostly going to be focusing on the chemical properties of matter. So first, let's talk about the physical properties of matter. So physical properties include anything that you can observe with your 5 senses. Your eyes, your sight, your taste, your smell, your touch, and your hearing. So those are your 5 senses. You can observe these things very easily. For example, if I look at a table, I can see the color of the table. For example, the table I'm sitting at is blue. That is a physical property. I can also observe the hardness. This table is pretty hard. The texture of the table is smooth because it was sanded over, and etc. These are examples of physical properties. And physical properties are mainly defined because they can be changed by physical means. The difference between physical changes and chemical changes, which we'll be talking about, is that chemical changes actually change the composition of the substance. So you're actually going down to the atomic level and you're changing the way that these atoms bond. So at the end of the day, you're changing what the substance is. You're changing its properties. But in physical change, the substance does undergo some kind of change, but at essence, it's still the same substance. So my best example to you would be water. For example, when we freeze water, we get an ice cube. When we melt water, we get just water, like liquid water. And then when we boil water, we get water vapor or gas. But at essence, we still have those water molecules, those H2O molecules. We're not changing those molecules. We're not breaking any of the bonds between the 2 hydrogens and the oxygen. Therefore, all that I just described, the freezing, melting, and boiling, those are all physical changes. Other examples include cutting. For example, if you cut an apple into smaller pieces, you're not changing the substance of the apple. You're not changing the composition of the apple. You're just breaking into smaller pieces. Bending something. For example, if you bend a straw, you're not changing the actual composition of the straw. You're just changing its shape. This also includes dissolving. So, for example, if you put salt in water, water will actually dissolve the salt, but this is actually not a chemical change. This is a physical change. Another example would be when you're putting hot chocolate mix in milk, and then the hot chocolate mix dissolves in the milk. Those particles are just being surrounded, those particles are called the solute, and then what's doing the dissolving, for example, would be the water or the hot milk. That's the solvent. We talked about that in the last video, but that's another physical change. Then, like we said, freezing, boiling, and melting with water, etc. So The simplest way I could put it is a physical property, is how something appears. So something you can easily see, because a lot of us rely mostly on our sight. So mainly what you can see. So what you can easily observe using your five senses, how it appears. An example of this would be iron, and I'll actually show you a picture of iron. Iron is an element on the periodic table, and you probably all are familiar with iron because it's used from everything from technology to weaponry to all these different substances. Like it's present in our everyday life. So examples of physical properties would be things like the color. It's a silver gray metal. Its hardness. It's a relatively soft metal, so it's not very hard. And then it's ductile. So a ductile means it's easily bendable. So those are all physical properties that I can observe without actually changing the composition of iron. So I'm not changing iron into something else. I'm not changing it into another element. It's still iron, but I can still observe all of these characteristics without changing it into something else. Now we have chemical properties, and this is chemical properties and the chemical part of these substances is what this video is going to focus on. So chemical properties include things like flammability. So how likely is an object to catch flame? For example, burning wood. Wood catches fire pretty easily, so it has high flammability. You have toxicity. So toxicity is pretty much a measure of how harmful a substance is to organisms or the environment. So toxicity mainly looks at the chemical composition of a substance, and depending on the way that atoms are bonded in that substance to make up the substance, that can determine how toxic the substance is. For example, carbon monoxide. You all have heard of that. That is a very toxic gas. So toxicity is an example of a chemical property of carbon monoxide. You have reactivity. So I think this is pretty straightforward. If something is going through a chemical reaction, its composition is being changed. So how reactive a substance is a chemical property, because it's going to tell you is this substance going to react with something else? How likely is this substance to change itself or change another substance? Things like that, and so on. So, of course, chemical properties can be changed by chemical means only. That's where you're changing the actual composition of the substance. Examples are burning of paper. You're changing the paper. You can't change it back. Think of it that way. That's a good way to think of it for beginners. You can't change something back. That is a good example of a chemical change. So you have burning of wood. You have digestion. So the hydrochloric acid in our stomach dissolves the food we eat. You have fermentation, which is a process by which microorganisms like yeast and bacteria break down bigger molecules. That is an example of a chemical change, and we'll talk more about that when we talk about metabolism and cell energetics later on. You have oxidation. Oxidation is pretty much when oxygen is involved. You have oxidation and reduction. So reduction is when an electron is added to a substance. Oxidation is when you take an electron away from a substance. So you're taking an electron away, so you're actually changing the chemical composition of the substance. So it's a chemical change. You have cooking, for example, baking, things like that. That involves fire. That involves changing elements, the chemical composition. So again, to change the chemical composition, a good example would be that iron combines with oxygen. So over time, you've probably seen anything iron. If you leave it outside, it'll react chemically with oxygen, and it'll form something called iron oxide, which is known as rust. So I just want to show you a picture of iron down here. So here are the properties of matter. So let's go to the next slide. Here are chemical changes. Let me just show you all of it at once. So chemical changes involve the breaking of bonds and the formation of new ones. So remember, atoms can form bonds between one another, and then when these atoms form multiple bonds, they can form these larger substances. And chemical changes pretty much occur when you change so these atoms bonded together represent the chemical composition of a substance. I think that's pretty straightforward. A chemical change occurs when you're trying to transform something, when you're trying to make it different. So to make a chemical change occur, you're going to be severing the bonds between these atoms. So this involves maybe the breaking of bonds, but on the flip side, a chemical change can also occur when you're creating a new bond. So maybe you have a carbon atom bonded to an oxygen atom. That's carbon monoxide. Maybe you end up bonding another oxygen to that carbon. So that is undergoing a chemical change because you were forming a new bond between the atoms. You're going down all the way to the atomic level and forming new bonds between the atoms, and then you end up getting CO2, carbon dioxide. So that would be a chemical change. Examples include burning, souring, digestion, cooking, baking, rusting, etc. Those are things we went over on the last slide. Chemical reactions are very, very similar. So chemical reactions are pretty much chemical changes, but when we talk about chemical reactions, we actually talk about the action occurring. So chemical change might be like, I burned this. This soured. I digested this. Chemical reaction is more like saying this atom bonded to this atom, if that makes sense. So you're going down all the way to the atomic level and describing what exactly is happening to change the substance's composition. So that's what a chemical reaction is. You have two types of chemical reactions. You have chemical synthesis or chemical degradation. I can't even pronounce this word properly. I'm sorry. This call it degrading. Chemical degrading. So synthesis pretty much means building up. So you are forming bonds. You are building a larger molecule with smaller molecules. Degrading pretty much means breaking down. So you have a larger molecule and you are splitting that molecule up and you're breaking it down. You're breaking it down further. So a good example of this, you probably don't know this because we haven't gone through metabolism yet. But an example of synthesis would be something like in photosynthesis, where we actually form glucose. Whereas degrading would be something that occurs in cellular respiration, where that glucose molecule is broken down so we can form ATP, which is usable energy in the body. So those are examples of chemical reactions. So here's a chemical formula, what a chemical formula is. So a chemical formula are symbols that show the kind and number of atoms in a compound. So chemical formulas you've probably seen, for example, you see already here H2O and HCl. You pretty much abbreviate, so to represent what atoms are present in a compound or a molecule in this case, you would just take the abbreviation, which is just the chemical symbol from the periodic table, and then you would use that to indicate which atoms are actually present in this substance or compound, and then you would represent how many of those atoms are present. So these symbols show the kind and the number of atoms in a compound. So my first example for you is H2O. So H2O molecules down here, this big red atom is oxygen. These two smaller ones are hydrogen. In 5 H2O molecules, there are 5 water molecules. So remember, H2O is 5 water molecules. I think this is pretty straightforward. We all know that H2O is water. So in 5 H2O, there are 5 water molecules. Out of these 5 water molecules, each water molecule has 1 oxygen atom and 2 hydrogen atoms. This can be indicated because if you look down here at this 2, we're going to be talking about the subscripts and coefficients soon, but this 2 indicates that there are 2 hydrogen atoms per water molecule and 1 oxygen atom per water molecule. So because there are 2 hydrogen atoms per water molecule and we have 5 water molecules, we technically have 5 times 2 hydrogen atoms. So we have 10 hydrogen atoms because we have 1 oxygen atom per water molecule, and we have 5 of those water molecules, we have 5 oxygen atoms. So if we add the 10 hydrogen atoms to the 5 oxygen atoms, we get 15 atoms total. So here's a second example. It's down here. It's HCl, which is hydrochloric acid. This is what's found in our stomach, and it's used in digestion to break foods down. So this right here, this big green atom, it's actually chlorine, and this smaller white atom is hydrogen. It's actually the same white atom as in this diagram of water. So in HCl, there are 3 molecules of hydrochloric acid because in 3HCl, there are 3 hydrochloric acids. So each HCl is 1 hydrochloric acid. 3 of them are 3 hydrochloric acid. If we see here, we have 1 hydrogen atom per hydrochloric acid molecule. Therefore, because we have 3 hydrochloric acid molecules, we have 3 times 1, which is 3 hydrogen atoms. And we also have 1 chlorine atom per hydrochloric acid molecule. Because we have 3 hydrochloric acid molecules, we have 3 times 1, so 3 chlorine atoms. If we add the 3 hydrogen atoms to 3 chlorine atoms, we have 6 atoms total. So that is interpreting chemical formulas. Now let's talk about chemical equations. So chemical equations represent the chemical proportions of atoms and substances that have undergone reactions. So we're talking about chemical reactions here, where especially chemical reactions where, in this case, like for this example here, we are combining two atoms to form we're synthesizing we're synthesizing two substances to form a larger substance. So it's synthesis. In other cases, you might see a substance being broken down into two other substances. So these chemical equations, like the one you see here that says Fe plus O2 equals Fe2O3, these represent the chemical proportions of atoms. So how much Fe is in this, how much Fe is in the substance, how much O2 is in the substance, and this plus sign indicates that they have undergone a reaction. So an example is the rusting of iron. Like we said, when iron reacts with oxygen, forms iron oxide or rust. So this is the actual chemical equation that represents exactly what's happening. So the reactant, so what this pretty much tells you is one reactant plus another reactant equals a product. Remember, a reactant is what is going into the chemical equation, and the product is what's coming out of the chemical equation. So the reactant, one of the reactants here is Fe, which is iron. The other reactant here is O2, which is oxygen. So when you add these two together, you're going to get the product, which is Fe2O3, which is iron oxide, which is rust. So the reactants here, like I said, are iron and oxygen, and them combined together. This plus sign indicates that they're being bonded together in this chemical equation. The product is on the right side of the equal sign, and the product here is iron oxide, which is Fe2O3. I think that's pretty straightforward. So now let's talk about subscripts and coefficients. So the example that I'm going to use is very similar to what we saw on the last slide when we saw Fe plus O2 equals Fe2O3. In this case, we have four iron. So the example here is we have four iron atoms and we have three oxygen. We have three O2s, and this is going to give us two Fe2O3s. So two molecules of iron oxide or rust. So don't get all caught up with the subscripts. Don't get caught up with what the numbers are. Try to understand what they represent. So I'm going to explain what I mean by that. So understand what the subscripts are and what the coefficients are, instead of understanding why is the subscript equal to this, why is the coefficient equal to this. We'll talk about balancing equations soon, but you really don't need to worry about that yet, really, until you get to chemistry. So subscripts are the small numbers to the right of each element. So subscripts, think of sub as below. So sub is below, sub is small. So subscripts are these small numbers right here. For example, with this 3O2, the 2 would be a subscript. And this Fe2, 2 would be a subscript. And O3, 3 would be a subscript. So these indicate how many atoms of that element are present. So example, in 3O2, we have two O2 atoms, and you multiply that times 3, so we have 6 total oxygen atoms. Here in this Fe2O3, we have 2 iron atoms. We multiply that times 2 because we have 2 molecules of this. We have 4 iron atoms. So that's what they indicate. They indicate how many atoms of that element are present. Instead of writing 2 FeO3, we abbreviate that by saying 2 Fe2O3 to indicate that, if that makes sense. Now we have coefficients. So the large numbers to the left of each element are compound. For example, the 4 in front of the Fe here is a coefficient. The 3 in front of the O2 is a coefficient. The 2 in front of the Fe2O3 is a coefficient. While subscripts indicate how many atoms of an element are present, the coefficients indicate how many molecules are present. So in this case, I know this is written kind of weird for Fe, but this pretty much means that the Fe's are not really bonded together. So again, don't worry about that. That's more chem stuff. But I want you to focus more on this 2 Fe2O3. So Fe2 and O3 are bonded together. But this 2 in front of it indicates that we have not one molecule of iron oxide. We have 2 molecules of iron oxide. So that's what a coefficient will represent, how many molecules of that substance are present. Here's another good example with hydrogen reacting with oxygen to form water. So the coefficients are, so we have 2H2 plus O2 is equal to 2H2O. So the coefficients are here. For example, we have 2H2 so we have 2H2, and then here we have 2H2O. So we have 2 water molecules here. We have 2, I'm trying to remember the name of, we have two sets of 2 hydrogen molecules bonded together. So hydrogen molecules usually bond together, so they come in pairs. So we have 2 sets of 2 hydrogen atoms each. So we have 2 here, we have 2 here. So that's pretty much what it means. Here we have the subscripts. So in each pair we have 2 hydrogen atoms, obviously. And here we have 2 oxygen atoms bonded together, and here we have those 2 hydrogen atoms. So again, this indicates how many of each atom is present. So those are subscripts and coefficients. Now let's talk about balanced chemical equations. So the number of atoms on each side of the equation must be equal. And this is because mass is neither created nor destroyed during the chemical reaction. This is the law of conservation of mass, I believe. Yes. So this pretty much indicates, you all know, that mass cannot be created nor destroyed. It can only be converted and transformed into other forms of matter. For example, when you have wood and you're burning the wood, the ashes you get as a result have a much lower mass than the actual wood you burn. And that when you burn the wood, it's a chemical reaction. So the ashes you get have much less mass than the wood. So you're probably thinking, in that chemical reaction, some of the mass of the wood was destroyed when it was burned. But the answer is no. You've probably seen the smoke that is emitted by the fire, and that contains carbon dioxide and oxygen and even some molecules of water. And that's where the rest of the mass is found. So mass is never created nor destroyed, it is just converted. Therefore, when we're writing these chemical equations, whenever we have the reactants, the number of atoms we have in the reactants must be equal to the number of atoms we have in the product. It must be balanced, because it must show that none of the atoms were actually lost or destroyed. And at the same time, if we're breaking a molecule down, or even building another molecule, we can't have more atoms on the right-hand side than the left-hand side, or the left-hand side than the right-hand side, because that shows that atoms were created, and you can't just create atoms, because that's not a property of mass. Matter always has to be balanced, and that's what this means by balanced chemical equations. So, for example, 4Fe plus 3O2 equals 2Fe2O3. Even though this might look a bit funky, this is a balanced chemical equation. Energy is absorbed when bonds are formed. When bonds form between atoms, they actually consume energy. So when these bonds are formed, energy is consumed. When these bonds are broken, energy is released. And I think you'll understand this better when we get to metabolism and we get to ATP, which is a high energy molecule, and the breaking and formation. So when ATP forms a bond, it actually gets more energized. When it breaks a bond, it releases a lot of energy and becomes de-energized. And even though this energy transfer is happening, the number of atoms is never changed. So even though, for example, ATP is forming these bonds and breaking these bonds, you're still going to have those same atoms. It's just like, if you think of it like this is one atom, these are these are other atoms, and these were bonded together. But then when I broke them, I released energy. But this atom over here, it was not lost. It still exists. And if this atom bonds to this larger molecule, we didn't just create an atom. That atom already existed. So that's what I'm trying to get at here. So here we have another really good example. I think I took this from WikiHow. We have C3H8 plus 5O2 is equal to 4H2O plus 3CO2. So C3H8 is propane plus oxygen is equal to water plus carbon dioxide. So what they're trying to show us here is that on this left-hand side of the equation, we have carbon atoms, we have hydrogen atoms, we have oxygen atoms. So we have 3 carbon atoms, as we can see by the subscript. We have 8 hydrogen atoms, as we can see by the subscript, and then 5 O2. So we multiply the 5 times the 2, we get 10 oxygen atoms. On the right-hand side of the equation, we have 4 H2O plus 3 CO2. So let's start with let's start with the C, actually. So because there's only 1 carbon atom per carbon dioxide molecule, we have 3 carbon dioxide molecules. We have 3 times 1, which is 3 carbon atoms. Then let's look at the hydrogen. We have H2, and we have 4 molecules of H2O. And per molecule of H2O, we have 1 H2. So we're going to multiply 4 times 2 and get 8. And lastly, we have O. So 4 times oxygen here. There's no subscript, so we can assume it's 1. So 4 times 1 is 4. But then over here with carbon dioxide, each molecule of carbon dioxide has 2 oxygen atoms. We have 3 molecules of carbon dioxide, so we do 3 times 2 is 6. 4 plus 6 is 10. And if you see, it's circled and checked off to show that we, even though this chemical reaction has occurred, the equation is balanced, because on both sides we have 3 carbon atoms, we have 8 hydrogen atoms, we have 10 oxygen atoms. Each stayed the same. We didn't add new atoms out of nowhere, and we didn't destroy any atoms, or we didn't lose any atoms. So finally, let's talk about what atoms are. Atoms are the smallest parts of matter, like I told you before. They're the smallest things that constitute matter. They're like the building blocks, if you want to think of it that way. They're even smaller than a cell. They're the smallest defining feature of an element that retains its properties. If you don't get what that means, it's fine. We're going to go into it in the next video. But each element is represented by an atomic number on the periodic table. And that atomic number indicates how many protons are in the nucleus of an atom representing that element. So the amount of protons in that nucleus defines what element that atom belongs to. If you go down to the subatomic level, if you look at protons, electrons, and neutrons, they're not specific to certain elements, meaning they are just general to any element you can find on the periodic table. So the atom is the smallest defining feature of an element that still retains its properties. For example, its reactivity properties and just things like that. Let's talk about the nucleus now. So the nucleus is a positively charged center of the atom. It is the densest part of the atom, and here you can find subatomic particles like protons. Protons have a positive charge. They're represented by a plus sign. You also have neutrons, and neutrons have no charge. They are neutral. They're often represented by a 0. You'll also see like a slash through the 0. I didn't write that, but you can either have a 0 or slash through the 0. So the nucleus is constituted of the protons and the neutrons. It's positively charged because remember the neutrons have a 0 charge and the protons have a plus charge. So if you have 0 and a plus charge, the plus charge is obviously going to dominate. So you have a positively charged like core of the atom. And finally, you have electrons, which are very, very important in bonding and reactivity. These are negatively charged particles surrounding the nucleus. So they are not part of the nucleus. They actually dart around the nucleus in these shells or orbitals, which we'll talk about in the next video. So if you look at this picture right here, this really bright center is the nucleus. As you can see, it's like the densest part of this atom. And then these spinning things right here, like these disks that seem to go around there, those are the orbitals. And these glowing things right here, they're these electrons that are moving so fast. These electrons are very, very small particles. They're about 1,800 times smaller than a proton, I believe, but they're highly charged atoms. Subatomic particles. Now we have protons. Let's talk briefly about protons. Like I said, they have a positive charge represented by a plus sign. They're found in the nucleus along with the neutrons. They form that positive dense center of the atom. The number stays the same in an atom because it defines the element. So like I said, the atomic number, every element has a specific atomic number. So it has a specific means unique. Whenever you hear the word specific in science, it means unique. So each element has a specific atomic number. And the atomic number represents the amount of protons in the nucleus of that atom. If we end up changing the amount of protons in the nucleus of an atom, we are essentially changing what element it is. For example, a hydrogen atom has 2 protons in its nucleus because its atomic number is 2. If we end up adding a proton to the nucleus, it's no longer a hydrogen atom, it's a lithium atom. And lithium has an atomic number of 3. So it has 3 protons in its nucleus. That's why the number of protons will never change in an atom unless it undergoes a chemical reaction that specifically changes the protons. Otherwise, the number of protons will change in an atom because it actually defines the atom. So it defines the atom as being a part of this element and representing this element. So it's the same number as the atomic number I said. So protons, you can always find out the amount of protons in an element by looking at the periodic table and finding that element's atomic number. And here on this diagram, you can see the protons are in blue. So they're in this dense positive center of the atom. Next, we have neutrons. So neutrons are uncharged or neutral. Like I said, they have no charge at all. They are neutral. You can think of putting a car in neutral. It's not really you're really not in control of it. So it's kind of uncharged. It's in that neutral state. You don't really think of you being neutral. So like, you don't really have, if you feel neutral about something, you don't really care. Not that you don't care, but you don't feel anything towards it. So in this same case, uncharged or neutral means 0 charge. So it's found in the nucleus along with the protons. Like we said, it's part of that positive dense core, and combined with protons, it equals the mass number of the element. So the mass number we'll talk about also in the next video. The mass number is equal to the amount of protons plus the amount of neutrons in an atom. Just talks about the amount of mass, the amount of space that atom takes up, the amount of matter that is in that atom. Obviously, atoms with larger mass numbers are going to be larger atoms. And the reason we don't include electrons in mass number is because they are just so small and insignificant, they really don't add anything to the mass number. So combined with protons, they equal the mass number of the element. Here we have a neutron in this diagram, this red subatomic particle. It's clustered with the protons, and together they cluster together and form this ball-like core in the middle of the atom. And they make the densest part of the atom. And lastly, we have electrons. So electrons have a negative electrical charge, like we said before. They're found outside the nucleus. They're farther from the protons and neutrons. So they go in these orbitals, or these like disks that surround the nucleus where the protons and neutrons are found. And then remember, opposites attract. So because the electrons have a negative charge and the protons have a positive charge, the electrons will never leave the atom unless a chemical reaction occurs. But they're pretty much attracted to the nucleus because the protons are there. So they're attracted to the protons in the nucleus, and they will just keep orbiting the nucleus because of that attraction. So they're still found outside the nucleus, though, so they're farther away from the center. They're found in energy levels. So as you can see, these disks kind of represent orbitals, and we'll get further into that in the next video, but I really want to leave that for chemistry because that is a whole unit in chemistry. You talk all about electrons and things like that. So energy levels are just fixed distances from the nucleus in which an electron can be found. So it's like shells. So you want to think of a nucleus as the yolk in an egg, and then you want to think of the eggshell, but think of multiple eggshells, not just one eggshell around the yolk. Think of multiple eggshells, and each of those shells are different distances away from the nucleus. So like the outermost shell is the farthest from the nucleus. The innermost shell is the closest to the nucleus. So these are fixed distances from the nucleus in which you can find an electron, and electrons can be found in any of these shells, just depending on the amount of energy an electron has. If the electron jumps between the shells, just things like that. And lastly, if an atom is neutral, then the amount of electrons equals the amount of protons. So think about this logically. If an atom is neutral, it has an overall charge of 0. So in this case, we don't really take into account the neutrons. So altogether, the atom has a charge of 0. So let's think about an oxygen atom. An oxygen atom has 8 protons. So if we want to have a neutral oxygen atom, we have 8 protons, and that gives us a +8 charge. So we have a high positive charge. We want to bring that down to 0 to make the atom neutral. So what do? We add 8 electrons, which are a -8 charge. So +8 minus 8 is equal to 0. So when an atom is neutral, you'll have the amount of electrons equal the amount of protons. This is not always the case, and we'll talk about that in the next video. Usually when you find a neutral atom, you will have an equal amount of electrons and protons. So if that's the case, you can literally just determine the amount of electrons in an atom depending on the amount of protons there are if you're given a neutral atom. That's all I have for you today. I hope you enjoyed that lesson, and please look for atoms, bonding, and molecules part 3. And afterwards, we're going to get an ionic and covalent bonding, just so you understand how these bonds are formed between atoms like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that we're going to be working with biological macromolecules. Again, I hope you enjoyed that video. If you did, please give it a like. Please subscribe to the channel. Drop a comment down below. Hit the post notification. Share using our socials, and do all of the things. And our socials are Facebook, Twitter, Instagram, all of which can be found in the description box below. You can also find our website in the description box. We're currently developing it, but I think it has substantial material for all of you. It is very, very cool if you want things like notes and quizzes to go along with all of our video lessons, so please check it out. And lastly, contact us at eCoreAcademy@gmail.com if you wish to. We will definitely get back to you. Again, that's all I have for you today. Please look out for my next biology video. Have a great day. Bye.